So I'm going to talk about codes and the world they live in, and in particular self-dual codes, because they are connected with many other parts of mathematics. This is one of the propellers that makes mathematics go forward. It's a bit like those maps of Australia, which show Australia at the center of the world and everything else spread out around it. From a certain point of view, if you are interested in self-dual codes, then you look out and you see that it's connected. They are connected to many other things. Obviously communications for error correction, and combinatorics because they're related to block designs, and group theory on various levels. These tend to be very nice symmetric objects, so they tend to have large groups. And they also are associated with various polynomials called weight enumerators, which are invariant under various groups. So we'll see quite a bit about that. Most of my talk will be about this lobe of the propeller. But if I was giving a second talk, I would talk about the same things, but lifted to lattices, quadratic forms and sphere packings. And there, instead of weight enumerators, we have theta functions of lattices, we have modular forms, we have Diophantine equations, and we have a lot of number theory. There are also connections with quantum error correcting codes that were quite miraculous when they occurred, and I've talked about that here a couple of years ago. I'm not going to mention much about that today. Another lobe is that they're connected with vertex operator algebras and string theory, and as Professor Lepofsky can tell you, many other things. And a long way out in this direction, there is a Fields medal, Richard Borchard's, which in a way you can say started off at the center of these things. So error correcting codes, they come up in all the years I spent at Bell Labs, they come up in error correction in transmitting data down a noisy wire. So the standard model is, you have a channel, the simplest channel of all, is the binary symmetric channel. You send zeros and ones, and you hopefully receive zeros and ones. And we pretend here that nothing gets lost. You send a zero, and 99% of the time you get a zero out. But 1% perhaps you get a 1 out. So there is a small probability of errors. And symmetrically, if you send a 1, usually you get a 1, but sometimes you get a 0. So this is the channel, and we're faced with the problem of sending a lot of information, bank statements and things like that down this channel. It might be a telephone wire, it might be a disk that we're writing on and reading later, or there are many other possibilities. It could be a camera sending pictures from Mars. There are many, many models where this applies. So we have many important messages, and we want to send them as quickly as possible and as reliably as possible. We would like the error probability to be very, very tiny. Maybe we'll allow 1 part in 10 to the 12 or something. But we want to cut it down from 1 error in every 100 transmissions to essentially 0. And so the solution is we only send certain strings of zeros and ones, called code words. We restrict how we use the channel. And so here's a very simple example of a code. And here is the picture. This is kind of the coat of arms of coding theory. We have the channel, we have noise coming in, we have a sender and a receiver, and we put in a coder, an encoder, and a decoder. So here's a simple example. If there were 2 messages, yes and no, you could translate yes into 5 zeros and 1 into 5 ones. So the code book has just 2 code words. And if, for instance, you receive 01001, you look at that and you say it's more likely, since errors don't occur very often, it's more likely that we send 5 zeros than 5 ones. It's closer in some sense, and in a precise sense, Hamming distance. We look at the number of places where it differs. It differs in 2 places from 5 zeros, 3 places from 5 ones. So the crucial thing is how close 2 code words are to each other. The minimum distance between code words in Hamming distance. And if that's d, then the spheres of radius integer part of d minus 1 over 2, they're disjoint. So by the triangle inequality, these spheres are packed in so they don't overlap, and as long as you don't make more than d minus 1 over 2 errors, you can correct the errors. And this is a distance 5 code, this example, so it can correct 2 errors. And the problem then is that we're given, if somebody tells us what the length is and how many messages we want to send, we want to maximize d. Or conversely, if d is specified, we want to maximize the number of code words with a given length. So this is the essential combinatorial question in coding theory. These spheres of radius d minus 1 over 2 around the code words are disjoint. It sometimes happens that these spheres of radius d minus 1 over 2 are actually not just a packing, but also a partitioning of the space. A covering, if you like, that everything is in one of the spheres. There are no crumbs. If it's a cake and these are spheres, there are no crumbs left over. So these are called perfect codes. And there are lots of nice number theoretic questions that are still unsolved, having to do with the classification of perfect codes. And I recycled a couple of old transparencies for this talk, and these white lines here are reflections from the scanner. I just included this just to show you a code, a real-life code. This is a code of length 3, where we take 3 message bits, U1, U2, U3. You've got 8 messages you can send now, binary vectors of length 3. We code them up. We start off by including the message bits, the 3 message bits, and then we add some check bits. So here's a simple example of a code of length 6 with 3 information bits. So we send the 3 bits that were put out by the source, and then we follow them by 3 more bits. So the 4th bit is the sum of C2 and C3, 5th bit is C1 plus C3, C6 is C1 plus C2. So we send 6 bits. Instead of 3, we add a redundancy. And that makes this into a code of length 6. It has 8 code words, and it's got minimum distance 3. It can correct 1 error. So if the message was 100, the code word would be the 100 followed by the 3 check bits. And that's actually an optimal code of its length. Now, codes, to start with, a code is just a subset of binary vectors of length n. But it could also be a subspace. It could be a vector space. It could be closed under addition mod 2. In that case, it's called a linear code. And that example I just showed was a linear code. And so was the one of length 5. Closed under addition mod 2. 1 plus 1 is 0. So if we have a linear code, we can define the dual code, C_perp. And C_perp is the set of all vectors in the space which have inner product 0 with all the code words. So they're perpendicular to all the code words. So here's an example. Take the little code of 5 zeros and 5 ones. What's perpendicular to that? Well, if we're going to have a dot product of 0 with 5 ones, we better have an even number of ones. Conversely, if we had an odd number of ones, we won't have a dot product of 0. So the dual code is all vectors with an even number of ones. And there are 2 here. The length we're working in is 5. 2 to the 5th over 2 is 16. So the dual code has 16 code words. In general, the C_perp, the size of C_perp, is the size of the field raised to the nth power, in this case equals 2 to the n over c. And if it happens that C is contained in its dual, then we say the code is self-orthogonal. And if it's equal to its dual, we say it's self-dual. Now this seems a bit strange perhaps, but you can do this with finite fields, where you can have a vector which is perpendicular to itself without having length 0. Because 1 plus 1 is 0. So in this example, so here are some examples of self-dual codes. The little code 0011, that's the smallest non-empty self-dual code. 2 code words of length 2. 2 other examples, classical examples, are the Hamming code of length 8 and the Golay code of length 24, which I will now show. show you another recycled view graph. So this is a more interesting code. This is the Hamming code of length 8. Dick Hamming, my former colleague. Much of this work was done by former colleagues of mine. A former colleague at Bell Labs. It's essentially a single error correcting code of length 8, or you can also look at it as a code of length 7. And here is a definition of this code. It's got length 8, and 8 minus 1 is a prime, 7 congruent to minus 1 mod 8. And that's a very nice thing to have. So with the way we construct this, which generalizes, we look at the squares, mod 7. So 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9, which is 2 mod 7. So the squares mod 7 are 0, 1, 2, and 4. And we build up the code by the first code word. We put 1s under the quadratic residues, mod 7, under the squares, mod 7. So we put 1s in position 0, 1, 2, and 4, 0s in the other position, and we add an overall parity check to make the total number of 1s even. We add a 0 here. And we take cyclic shifts of this. So this gives us 7 code words plus the 0 word. We're getting a linear code, so we're certainly going to have the 0 code word in there. We also throw in the all ones code word, and we then make it closed under addition, so we get the complements of all of these. So altogether we get 16 code words. We have the 0 word, we have 7 words with 4 1s here, and we have 7 more words with 4 1s, which are the complements of these with a 1 in the last coordinate. So altogether we get 16 code words. We can look at this in many other ways. This is the first code in many constructions of code. So the simplest non-trivial quadratic residue code. So we've used the squares, the quadratic residues mod 7. It also comes up from the projective plane of order 2, a picture you've seen a million times, the Fano plane. We've got 7 points, 7 lines. Any 2 points lie on a line, any 2 lines meet on a point. And
how did Hamming come up in the first place?
I don't know. I don't remember. I wasn't there then. It was 1949.
Maybe it was trial and error that we're experimenting.
Yeah. It's very easy to construct it in the following way. This is another construction of it as a Reed-Muller code. Here's a basis for this code with the coordinates in a different order. Suppose you want vectors of length 8, of 0s and 1s, that don't look like each other. Well, you would say, all right, let's put 0, 0, 0, 0, 1, 1, 1, 1. Very different from that is 0, 0, 1, 1, 0, 0, 1, 1. And very different from that is 0, 1, 0, 1, 0, 1, 0, 1, and then 1, 1, 1, 1, 1, 1, 1, 1. This is really a Hadamard matrix of order 8. And that's probably the first, the original definition. So to get that, you have to put the coordinates in a different order. But you can do that in many ways. So here are 2 different versions of the basis for a code which is equivalent to this code. So this is the projective plane of order 2. And this, if you write down the incidence matrix for this set of points and lines, you get this bottom 7 by 7 here. You get lines, there's a line containing the points 1, 2, and 0, 4, and 6, which is 0, 4, and 6. That's that vector. So this is the incidence matrix showing how points and lines meet in this plane. So that gives us this. We take the complements and we get that. Now, this property of having a line through any 2 points is a characteristic property of what's called a Steiner system. This is a Steiner system S237. It says we've got, one way to describe this is you have a faculty of size 7, you have committees of size 3, and the rule is any 2 professors must be on at most 1 committee. So any 2 points must be on exactly 1 line, belong to exactly 1 block of this block design. So that's this, it's a 2, 3, 7. If we look at all 7 plus 7 vectors of length 8, this is a Steiner system S348. This has the property, if you pick any 3 of the 8 coordinates, there's a unique code word out of these 14 code words with 4 ones that contains those, that has ones in those 3 places. And the order of this group, it's a very nice group. It's the, you can describe it in many ways. It's a familiar group of order 8 times 7 times 6 times 4. If you can coordinatize these by triples, and then it's the general affine group GA3, 3 by 3 matrices over GF2. So that's the Hamming code. Now, and that's based on the, it's a quadratic residue code based on the prime 7. If we do the same thing for the prime 23, we get the Golay code. And this is an analog of the bottom half of the previous slide. So here I've put zeros under the quadratic residues mod 23, which are in purple in the top line. So the first of the generators has zeros under the squares mod 23. And there's a 1 in the last coordinate. And we take all cyclic shifts of that, and we take their complements. And we look at the linear space that they span. And it turns out they span a 12-dimensional space. We're in 24-dimensional Hamming space. And this is a self-dual code. And it's the Golay code, Marcel Golay, about the same time, maybe 1949 or so. And again, there are block designs that come from this. If we look at all the vectors, we've got 2 to the 12th binary vectors. And there's the 0 vector. And then there are a lot of vectors that have 8 ones. There's nothing that has fewer than 8 ones in it. The minimum distance between code words is 8. So it's a triple error correcting code. 8 minus 1 over 2 is 3. You can correct 3 errors. The spheres of radius 3. In fact, this is another perfect code. Did I mention that the Hamming code is a perfect code? If I dropped this last coordinate, we've got 16 code words of length 7. If we look at spheres of radius, Hamming radius 1 around these, they exactly fill up the space. So deleting that column gives us a perfect code. Likewise, here, we again get a perfect code. Perfect codes are very rare. These are two of the best, 2 of the few linear codes. Anyway, so these 759, there are 759 vectors with 8 ones, code words with 8 ones. They're not lines in a projective plane anymore. They're octets. They have 8 points in them. There is a subset of size 8 out of a population of 24. They're committees, if you like, of size 8. And they have the property that any 5 faculty members any 5 you pick out of the 24 belong to exactly 1 committee, 1 octet. And so it's the Steiner system S5824. And its group is the Mathieu permutation group M24. Now, if I had another hour, I would talk about how we lift this into Euclidean space. The Hamming code of length 8 becomes the E8 root lattice. This, with a bit of twiddling, becomes the Leach lattice in 24 dimensions. And then we get to modular forms. And the reason the modular forms come in is that they're analogs of weight enumerators. So we want to give a secretary's report on the code. We want to tell how many code words there are in the code of each weight. So my little first example, 5 zeros and 5 ones, we describe it by saying there's 1 code word of weight 0, 1 of weight 5. So the weight enumerator is x to the 5th plus y to the 5th. The power of y tells you how many ones there are. It's like a generating function for the number of code words of each weight. It's dual. You remember it has 16 code words. It has 10 code words with 2 ones, 5 choose 2, and 5 code words with 4 ones, 5 choose 4. So its weight enumerator is x to the 5th plus 10x cubed y squared, meaning weight 2, plus 5y to the 4th, meaning 5 code words of weight 4. There should be an x in front of that. There's 1 0 and 4 ones in each of those code words. So that's the dual code. Now, there's a beautiful theorem by my former colleague Jessie McWilliams in her PhD thesis at Harvard in 1962. She proved the lovely theorem that you can get the weighted numerator for the dual code by a simple linear transformation of the weighted numerator of the code. You replace, this is the binary case, you replace x by x plus y and y by x minus y. If we were over a field of size q, it would be x minus q minus 1 times y. If we were looking at the Hamming weighted numerator. And the proof, this is a version of the Poisson summation formula. It's easy to prove, and you can express it by setting it up in the setting. If you have a subspace, the average of the Fourier transform of a function over the space is equal to the sum of the original function over the dual space. And if you define the right kind of function, namely a function which depends on the weight of a vector, and you use the right kind of Fourier transform, which is a discrete Fourier transform, then this falls out. And so, for example, if we took this x to the fifth plus y to the fifth and replaced x by x plus y and y by x minus y, so we get x plus y to the fifth, x minus y to the fifth, expand, divide by 2, the size of the code, and we get the weighted numerator of the dual code. Very nice theorem. Now, if we have a binary code and it's self-dual, every code word must have an even number of ones. If you have a vector which is perpendicular to a self-mod 2, it must have an even number of ones. Otherwise, okay. So that's automatic. A binary self-dual code implies that all the weights, all the Hamming weights are even. But the Hamming code has an additional property. All the Hamming weights are multiples of 4. And likewise, for the Golay code, we had 759 times x to the 16th, y to the 8th. We have, in the Golay code, the only weights that occur are 0, 8, 12, 16, and 24. And so in those two examples, the weights are divisible by 4, which is, well, that's nice. Let's tie these things up. There's a theorem due to Andrew Gleason and John Pierce from 1967 that says this doesn't happen very often, this property of having the weights divisible by some constant. So suppose we have a self-dual code over a field, Galois field GFQ, and all the weights are divisible by some number m bigger than 1. Then there are only, apart from some trivial cases, there are only 4 cases where that can happen. It can be a binary code, an ordinary self-dual binary code, and that automatically implies the weights are divisible by 2. But we are allowed to, if we want, we can say we can also have binary codes with the additional restriction that the weights are divisible by 4. That makes sense. You've seen 2 examples of that. We can also consider codes over GF3, ternary codes, and there it's automatic that a self-dual code has weights divisible by 3. And the only other case is codes over the field of 4 elements. Now here we have 2 different kinds of inner products we can use. Just the straight naive inner product, or the Hermitian inner product, where you take x times y bar, like taking the complex conjugate. If you look at the Hermitian inner product, then automatically the weight's divisible by 2. If you look at the Euclidean inner product, then you are allowed to impose the restriction, weight's divisible by 2. But these are the only 4 families, apart from some trivial examples. So people call these codes self-dual codes of types 1, 2, 3, and 4. So suppose we have a self-dual code. Let's look at what we can say about the weighted numerator using McWilliams transformation. McWilliams tells us that if a code is self-dual, it's fixed under the McWilliams transformation. It's fixed. It has the property that the weighted numerator of the dual code, which is the weighted numerator of the code, because it's equal to its dual, is the same, is what you get by replacing x by x plus y and y by x minus y. and dividing by the size of the code. The size of the code, though, is 2 to the n over 2, because it's half the dimension. The dimension is half the length of the space. So, and it's homogeneous. The reason we made it a homogeneous polynomial is precisely because we want to be able to take that 1 over 2 to the n over 2 inside, inside this polynomial, so we can say it's w of x plus y over root 2 times x of x minus y over root 2. So it's fixed, it's invariant under the linear transformation. Replace xy by the matrix 1, 1, the Hadamard matrix 1, 1, 1 minus 1 divided by root 2 times xy. It's fixed under that transformation. Now, if in addition it's got weights divisible by 4, that means we only get powers of y to the 4th in it. So it's fixed under replacing y by I times y. And therefore it's fixed under any combination of these transformations. So it's fixed under the group they generate, the multiplicative group that they generate. And this turns out to be a group of order 192, which is pretty big. I mean, it could have been a trivial group, but 192 is big enough that this is a very interesting situation. And when you're multiplying them out, you see that it has diagonal matrices in it, which have 8th roots of unity down the diagonal, 1 plus I over root 2. So this group has a center of order 8, diagonal matrices like that. And of course, that means that the length of these codes has to be a multiple of 8, because otherwise they can't be fixed under this transformation. Right? You replace x and y simultaneously by themselves multiplied by an 8th root of unity. If that's going to be fixed, then the length, we had to have a homogeneous polynomial whose degrees were all divisible by 8. So now we can bring in one of the very nice classical theorems from group theory, Marlenes' theorem from 1897, that says that if we've got a finite group of matrices, complex n by n matrices, and you want to study the ring of invariants, what polynomials are invariant under all the transformations in this group? Well, first of all, it is a ring, obviously, because if two polynomials f and g are fixed under the action of the group, so is their sum and difference and product. So it's a ring, and not just fixed globally, but fixed by every individual element in the group. So Marlenes' theorem says, let's look at the homogeneous invariance of degree d. If a polynomial is fixed, obviously its homogeneous parts must be individually fixed, because these linear transformations don't change the degree. So let AD be the number of linearly independent homogeneous invariant polynomials of degree d. Then Marlenes' theorem says the generating function for these numbers AD, summation AD lambda to the d, is essentially the average of 1 over the characteristic polynomials of these matrices. Precisely, it's the average of 1 over the determinant of I minus lambda m, summed over all matrices m in the group. And it's easy to prove, but it's very nice. So let me do in a simple example, look at a really trivial group, the group of 2 matrices, the identity matrix and minus the identity matrix of size 2. We can, first of all, work out what the invariants are. If it's fixed under those transformations, then it better have only even degree terms, monomials in it. So the invariants, obviously x squared is fixed, xy is fixed, and any invariant, you can write it, obviously, it's the ring generated by x squared and y squared. Any of those polynomials are fixed, and xy times one of those polynomials. There are really 3 generators, but they're not algebraically independent. There's xy, there's x squared and y squared. Any combination of them is fixed, and nothing else is fixed. That's the ring of invariants. So we describe this by saying it's a ring which is the direct sum of polynomials in x squared and y squared plus xy times such a polynomial. And now we can use Marlenes' theorem, work out the Marlenes series, the generating function, we've got two matrices. We work out the sum of the determinant of 1 over the determinant of I minus lambda times the identity. We get 1 minus lambda squared, we get 1 plus lambda squared. We add them up, cancel, and we get 1 plus lambda squared over 1 minus lambda squared squared. And here is the whole point. You mash that up with the ring. This corresponds. I can write it as 1 over 1 minus lambda squared squared, which describes, this is a generating function for all the monomials in this part of the ring. The y squared over 1 minus lambda squared squared corresponds to xy times x squared y squared. So we've got x squared and y squared, which are algebraically independent. They correspond to the two terms in the denominator, and then we have xy, which is not algebraically independent, which corresponds to this lambda squared in the numerator here. So in general, we want to do this in the general case, and we'd like to find what we can sometimes call a good basis for this ring of invariants. It's a set of things which have this property. What we want are n algebraically independent invariants corresponding to the terms in the denominator, and then some further transient invariants, if you like, which correspond to the terms in the numerator. So a good basis is n algebraically invariants plus t, say further invariants, phi1 to phi t, where phi1 is 1, such that we can decompose the ring of invariants as a direct sum of pieces, like this, where and this, if that's true, that implies that the Marlenes series is a polynomial in the numerator divided by a product of terms of the form 1 minus lambda to the d something. So the d's are the degrees of the algebraically independent invariants, and the e's are the degrees of the transient invariants. There are various theorems that imply that this always is possible. You can always do this. You can always find a good basis. You can also pull out your Zariski and Samuel. These are called homogeneous systems of parameters for the ring. This is for classical commutative algebra. So there's a theorem of Hochster and Eger, 1971, that says you can always do this in this case. These rings are Gorham's There are many generalizations of this theorem to other settings, but here everything is pretty easy. Namely, finite groups of complex matrices, characteristic 0. There's nothing especially mysterious here. Other settings, it is more mysterious. So good bases exist, so we can go ahead and look for them. And if we do run Marlenes' theorem on a group and find out that the numerator is 1, which suggests there's only one piece in the ring, well, that may or may not be true, but there's a theorem from Shepard and Todd from 1954 that exactly characterizes when the ring of invariants just has one piece, when it's a free ring with n generators. And that happens if and only if the group is what I call an Ugger. It's a unitary group generated by reflections, described by a Coxeter-Dinkin diagram. And these have all been classified. And so we know everything about the case when there's just a 1 in the numerator of the Marlenes series. But it doesn't work the other way around. It's